Hello and welcome back to Steven Data. In this video, as I said in the last video, we are going to talk about counting techniques, but the question is why? In many of the examples I've provided so far in previous videos, it was easy to determine the number of outcomes in each event. However, in more complicated examples, determining the outcomes in a sample space or an event becomes more difficult. Consequently, counting the number of outcomes in our sample space and various events that are used to analyze our random experiment may become impossible. So, to overcome this problem, we will use some methods called counting techniques. In detail, we will talk about three topics: multiplication rule, permutation, and combination. Okay, enough talking. Let's dive into the video to learn how to use these three helpful techniques. Unlike other videos, I want to give you the definitions first before diving into the examples. So let's get to it. Assume an operation can be described as a sequence of k steps, and the number of ways to complete step 1 is n1, and the number of ways to complete step 2 is n2 for each way to complete step 1, and the number of ways to complete step 3 is n3 for each way to complete step 2, and so forth. The total number of ways to complete the operation is n1 times n2 times n3 times n4 up to nk. Now, let's see an example. The design for a website is to consist of 4 colors, 3 fonts, and 3 positions for an image. Based on multiplication rule, we have 36 different designs for the website that come from 4 colors times 3 fonts times 3 positions. I know that the example was ridiculous, but that was good for the beginning. Anyway, let's see a better one. Assume a bag that contains 6 red marbles and 4 blue marbles. 2 marbles are drawn from the bag without replacement. We are interested in the probability that both marbles are blue. The first step is to label your events A and B. Let A be the event that the first marble is blue, and let B be the event that the second marble is blue. The second step is to figure out the probability of A. There are 10 marbles in the bag, so the probability of drawing a blue marble is 4/10. The third step is to figure out the probability of B. There are 9 marbles in the bag left, so the probability of choosing a blue marble is 3/9. And the last step is to multiply step 2 and step 3 together. That results in 4/10 times 3/9, that equals 2/15. I know that the example was about probability and we have not talked about it yet, but acknowledge it. The example was not that challenging. Now, let's spend our time with permutation. Permutation is another useful calculation, finds the number of ordered sequences of the elements of a set. Consider a set of elements such as S, which has 3 elements of A, B, and C. A permutation of the elements is an ordered sequence of the elements. For example, ABC, ACB, BAC, BCA, CAB, and finally CBA are all of the permutations of the elements of S. In fact, the number of permutations of n different element is n factorial, where n factorial equals n times n minus 1 times n minus 2 times n minus 3 up to 3 times 2 times 1. This result follows from the multiplication rule. In fact, a permutation can be constructed as follows. Select the element to be placed in the first position of the sequence from the n elements. Then, select the element for the second position from the remaining n minus 1 elements, Then select the element for the third position from the remaining n-2 elements, and so forth. Permutations such as these are sometimes referred to as linear permutations. In some situations, we are interested in the number of arrangements of only some of the elements of a set. In this case, we use a special kind of permutation that is called permutation of subsets, and its definition is the number of permutations of subsets of R elements selected from a set of n different elements is equal to n times n-1 times n-2 up to n minus r plus 1. That can be summarized as n factorial over n minus r factorial. And in probability, it can be denoted as this. Now, let's see an example. A printed circuit board has 8 different locations in which a component can be placed. If 4 different components are to be placed on the board, how many different designs are possible? Each design consists of selecting a location from the 8 locations for the first component, a location from the remaining 7 for the second component, a location from the remaining 6 for the third component, and a location from the remaining 5 for the fourth component. Therefore, based on our formula, we have 8 times 7 times 6 times 5, or 8 factorial over 4 factorial, that leads to 1680 different designs. Our scenarios for permutation are not finished yet. Actually, we have one left, and that is the case when we are interested in counting the number of ordered sequences for objects that are not all different. In this case, we have permutation of similar subjects that can be defined like this. The number of permutations of n equals n1 plus n2 plus n3 up to nr objects, which n1 are of one type, n2 are of a second type, up to nr are of an rth type, equals to n factorial over n1 factorial times n2 factorial times n3 factorial up to nr factorial. Now, let's see an example about the last scenario of the permutation. A hospital operating room needs to schedule 3 knee surgeries and 2 hip surgeries in a day. We denote a knee and hip surgery as K and H respectively. The number of possible sequences of 3 knee and 2 hip surgeries is 5 factorial over 2 factorial times 3 factorial, that equals 10. These 10 sequences can be summarized as this. Now, it's time to learn the last term, which is combination. In permutation, the order was important for us, but the problem is, what should we do when the order of choosing elements does not matter? In this specific case, we use combination that can be defined as this. The number of combinations, subsets of R elements that can be selected from a set of n elements is denoted as this, and its formula is defined as n factorial over r factorial times n minus r factorial. As always, let's see an example about combination. In our printed circuit board, we had 8 different locations in which a component can be placed. Now, if we have 5 identical components that should be placed on the board, how many different designs are possible? Each design is a subset of size 5 from the 8 locations that are to contain the components. Based on the combination formula, the number of possible designs is 8 factorial over 5 factorial times 3 factorial, that equals 56 different designs. But before wrapping up the video, there is an additional point that knowing it is necessary. In random experiment in which items are selected from a batch, an item may or may not be replaced before the next one is selected. This is referred to as sampling with or without replacement, respectively. But to clarify this statement, let's see an example. The following example uses the multiplication rule along with combination to answer a more difficult but common question for sampling without replacement. A bin of 50 manufactured parts contains 3 defective parts and 47 non-defective parts. A sample of 6 parts is selected without replacement. That is, each part can be selected only once, and the sample is a subset of the 50 parts. We want to know how many different samples are there of size 6 that contain exactly 2 defective parts. A subset containing exactly 2 defective parts can be formed by first choosing the 2 defective parts from the 3 defective parts. Based on the combination formula, the number of different ways this step can be completed is 3 factorial over 2 factorial times 1 factorial, that equals 3. Then the second step is to select the remaining 4 parts from the 47 acceptable parts in the bin. The number of different ways the second step can be completed is 47 factorial over 4 factorial times 43 factorial, that equals 178,365. Therefore, from the multiplication rule, the number of subsets of size 6 that contain exactly 2 defective parts is 3 times 178,365, that equals 535,095. Now, to wrap up the video, let's review again what we have learned so far about counting techniques. First, we learned that if we want to calculate the total number of ways that can complete a k-step operation, we use the multiplication rule. Then, we learned how to find the number of ordered sequences of the elements of a set with the help of permutation, and we expanded this to some specific scenarios like having identical elements. And finally, we learned how to find the number of subsets of R elements that can be selected from a set of n elements in the way that the order does not matter with the help of combination. And that is done. Congratulations! Now you know some information about counting techniques and you are able to solve complicated problems with the help of them. At last, if you liked the video, please hit that like button, and if you are interested in this kind of topic, please consider subscribing to this channel because these two keep me motivated to create these kind of content. By the way, if you have a question about this subject and anything related to probability and statistics as well as data science, comment it down in the comment section. I will answer them as soon as possible. I hope this video helped you a lot, and until the next video, happy learning!